Hello everyone, I'm Shuhao Zhang from Peking University. I'm very happy to present our work in Singapore today. Our work is about the optimization of VSA-based program synthesis, a generalized synthesis algorithm. Let's start with the background. Version space algebra, or VSA in short, uses a graph-like structure to represent program spaces. A node in the VSA represents a program space with same output. This figure shows a simple VSA. You can see there are three kinds of nodes. The two leaf nodes represent atomic programs with no operators. Program 0 and x belong to the same node since they produce the same output in this example. The drawing node at the middle layer combines the subprograms with the specific operators, constructing larger programs. You can see that the left drawing node represents the program space with program link 0 plus y and x plus y. The union node at the top merges program spaces with the same output. That means the two program spaces like in the drawing node have the same output. Here is the workflow of VSA-based program synthesis. VSA-based program synthesis follows program-by-example framework, where we synthesize programs from examples and semantics. As you can see, there are three examples and the corresponding semantics in our example. First, simple example VSAs are constructed from these examples and semantics. So, three corresponding VSAs are constructed. Then, these VSAs are intersected in some way together to get a final VSA. The essence of VSA intersection is the intersection of program spaces. After intersection, we will get a final VSA whose program space has programs in all simple example program spaces. Finally, a program from the program space of the root node of the final VSA is extracted as the synthesis result. In this example, x plus y and y plus x is the result program. Our work focuses on the VSA intersection process. This part of the course accounts for the vast majority of the entire algorithm. Traditional VSA intersection process is iterative. Single example VSAs are added one by one. To analyze the efficiency of iterative VSA intersection, we draw the trend of the number of VSA nodes in the intermediate VSA, since more nodes will lead to more intersection costs. As you can see, the curve is like a hill. The peak is higher than the resource limit on those challenge tags usually. So, constructing such a huge VSA on the peak or intersecting with it is unacceptable. So, when the curve forms a hill, there are two factors influencing the size of the VSA when new examples added. On the one hand, the equivalent program space in a VSA node are divided into some program space when new example added, making the size larger. On the other hand, fewer programs will satisfy all examples, making the size smaller. That concludes the background part. We propose the following optimization to the VSA intersection. For multiple VSA intersection, we propose multi-way intersection. For the intersection implementation, we propose bottom-up intersection. We combine these techniques plus some detailed optimization to build an efficient synthesizer called Mo. So, is there a way to avoid the huge intermediate VSA in the iterative intersection process? The answer is yes. We propose multi-way intersection, which merges multiple VSAs into one directly, making it possible to avoid a huge intermediate VSA in the iterative intersection process. Now, we need to focus on how to perform the intersection. Formal approaches choose top-down intersection. The intersection process starts from root. I made this animation to show the process of the top-down intersection. Here, we start from intersecting the two root nodes. Here, the left one is a union node, and the right one is a join node. When intersecting a union node with other nodes, we stack on the sums of the union nodes. When intersecting two join nodes with the same operator, as you can see, we do intersections on the corresponding operands. Intersecting two leaf nodes is quite simple. Just intersect the atomic point spaces directly. These nodes in purple represent empty point spaces, since we can't know which node is invalid until the leaf nodes are constructed. There are many invalid nodes in the result VSA when we perform top-down intersection, leading to low efficiency. Therefore, top-down intersection is not suitable to combine with our multi-way intersection, since the number of invalid nodes will explode when there are too many VSAs in the intersection process. We need to find a more efficient intersection way to combine with our multi-way intersection. So, to avoid constructing these empty nodes, we propose bottom-up intersection, which starts from the leaf nodes. Here is the animation. As the intersection starts from leaf, all nodes has corresponding valid programs. You can see that bottom-up intersection constructs fewer nodes in the same example. Now it's time to build a PBE solver based on these techniques. Can we use the multi-way intersection to intersect all VSAs directly? The answer is no. We have to face a huge overhead when there are too many VSAs intersected together. Our solution is to divide simple example VSAs into solver groups in the right figure. Firstly, simple example VSAs are merged into solver intermediate VSAs using the iterative intersection. Secondly, these intermediate VSAs are merged into the final VSAs using the multi-way intersection. Now, we have to deal with a limited number of VSAs in the multi-way intersection. If the intermediate VSA is small, the whole process will be efficient. However, grouping leads to a new problem. If there are too many examples in a single group, the intermediate VSA will reach the peak. Boom! One approach is to use partial examples for grouping, then add the remaining examples iteratively. However, too few examples will lead to the failure of tunneling through the hill. The ideal situation is a green line. The smallest intermediate VSAs are constructed. After merging these VSAs, the result VSA will fall to the right foot of the hill. We use a heuristic strategy to find the appropriate point. The following formula is used to estimate the final program space. A small final program space indicates passing the hill. Then we can convert to iterative intersection to deal with the remaining examples. Detailed information about the heuristic strategy can be found in our paper. Our intersection algorithm has some good theoretical properties. In comparison with top-down intersection, we prove that bottom-up intersection can handle commutative and associative operators efficiently. In comparison with observational equivalence, a generalized PBE solver, we prove it performs no worse than OE theoretically with a constant factor, and the evaluation will show that our algorithm performs better practically. You could get detailed information, including theorem and the proof, in our paper. Now comes the evaluation. The evaluation consists of 3 parts. Can we speed up VSA intersection? Can we speed up specialized VSA-based solver? And the ablation study of each component. Due to limited time, we will omit the ablation study in our presentation. You could view our paper to get this information. There are 3 solvers in the comparison. Our solver is MoFTA. It performs multi-way bottom-up VSA intersection with adaptive grouping. Raw VSA performs iterative top-down intersection. OE implements observational equivalence, a generalized synthesizer based on pairing duplicated programs with same output in bottom-up emulation. We chose these 3 domains from Sega's comp to construct the dataset. Here are the results on the circuit dataset. You can see that we saw more tasks with less time cost and fewer VSA nodes constructed, especially on those challenging tasks. These results prove the effectiveness of Mo. To verify that Mo can combine with other VSA-based solvers to further improve their performance, we integrate our VSA intersection implementation into Blaze, a specialized VSA-based solver based on abstraction refinement. Here is the evaluation result. The result shows Mo can accelerate specialized VSA-based solver like Blaze. Finally, let's make a summary of our work. We notice that iterative intersection will reach the peak of the scale hill, so we propose multi-way intersection to tunnel through the hill. We notice that top-down intersection is inefficient when combining with our multi-way intersection, so we propose bottom-up intersection to avoid these invalid nodes. That's all. Thank you for your listening.
All right, we have time for a question. Any from the audience? I have kind of a naive question for you. So you made a comparison at the beginning with grammars, and so I was thinking about syntax-guided synthesis, which is more of a specification than a solution technique. But what's the relationship between version space algebras and grammars?
Pardon?
What's the relationship between version space algebras like you did here and, say, a grammatical formulation of the problem? Do they cover different things? Are they similarly expressive, or are they completely different? Sorry.
Oh, the node in the node in the VSA, like the drawing node, you can see the plus node connects the subprogram and then build the bigger programs.
Okay.
Okay.
All right. Thank you.
Oh,
Let's thank the speaker again.